Good morning.
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 People are adding. I can see this on my screen. Okay. Today is April 22nd. I am planning to discuss with you your old material about inverse trigonometric functions, but I would like to say just a few words about graphs of tangents as a function, as functions. I am not planning to discuss other graphs, but they are also important, but mainly more often you will be dealing with functions from families of sines, cosines, and tangent. This is why I put more emphasis on that particular material. So if you like right now to start this review, I really like to ask you right now to write down the equation for tangent as a function. Let's actually talk about a basic tangent, which is y equal to tangent x. Let me write it down. Y equals to tangent x. And this is the old material from yesterday. But what would I like you to do? I would like to ask you right now to answer the following questions regarding that tangent x as domain of that function, range of that function, asymptotes for that function. And I will check attendance right now because people are still adding this conference, and I will join your company. Okay. Andrew,
Here.
Tima, Lorraine,
Here.
Lynn,
Here.
Juanita, Yuran,
Here.
Gabriel, Divina, Kobe, Chantal.
Here.
Guys, can you please reply? Yeah. So, Gongxi,
Here.
Kyle,
Here.
Matthew,
Here.
Julian,
Here.
Nathan,
Here.
Alejandro. Okay.
Here.
Thank you. Okay. Let's go back to y equal to tangent x. First, I would like to say that only two families of trigonometric functions have domains equal to set R, set of all real numbers. These families are families of sine and cosine. All other four trigonometric functions have domains not equal to R. What kind of angles should be excluded from set R for domain? Can you tell me, please? Let's even right now talk about just, let's say, a unit trigonometric circles. In one revolution, can you please name two angles for which tangent is undefined?
Pi over 2.
Pi over 2, did you say pi over 2?
Yeah, that's the first one.
What about the second?
3
3 pi
pi
over 2?
over 2.
Absolutely, yes. Can I say that these two are vertical quadrantal angles?
Yes.
Yes.
Besides that, do we know that if we have full revolution in addition the first one, so will be the second revolution, excuse me, we are going to come to same points on the circle?
Yeah.
In this case, can I say that it will be actually pi over 2 plus 2 pi times k, where k indicates how many times we rotate? And it
Yes.
will be 3 pi over 2 plus 2 pi k.
Yes.
Yeah.
But you know what? We can unite these two families of bad angles for tangent into one family, because actually tangent is pi periodic function. It is not like 2 pi periodic function as for other basic trigonometric functions like sine x, cosine x, secant x, or cosecant x. Tangent and cotangent, they are tangent x, I mean, and cotangent x. They are pi periodic functions. So which means if I'm talking about, let's say, tangent, I immediately can write down the information about angles which are bad for tangent. And I'm going to use that information about tangent being pi periodic. I'm going to show this to you right now. Let me just write it down. And you will see right now only one family of bad angles instead of two. I just said that. Look what I wrote down. Instead of pi over 2 plus 2 pi k, or 3 pi over 2 plus also 2 pi k, I wrote it only as a one family, pi over 2 plus pi times k. Each time moving from previous angle to another one on the distance of pi, which means pi over 2, let's say, plus pi, when k is equal to 1, it will be 3 pi over 2. If k is equal to 0, it will be just pi over 2. If k is equal to 2, it will be pi over 2 plus 2 pi, which will be 5 pi over 2, etc. Z here is the set of all integers. So we are getting infinitely many angles which we have to exclude from R to get a domain for our tangent X. So which means D, when it is a domain, equals to set R except all these angles which I just wrote down when I wrote X not equal to that angles. Look what I did. Set R except angles pi over 2 plus pi k. And I did not specify in this on this last line where this k is coming from, because I just had this information above that last line, that k belongs to z, and z is a set of all integers. But discussing this information has a very positive, this discussion has a very positive outcome as well, because now we can talk about asymptotes. And asymptotes here for tangent will be vertical asymptotes, and they will be running through all these bad points which we excluded from domains. So vertical asymptotes, they will be having the following equation. Because it is a vertical line, as any vertical line, it should have a form of x equal to the certain number. So all vertical asymptotes will be having the following equation, where k is from z again. Vertical asymptotes have this equation. There are infinitely many vertical asymptotes. They will be running through all these declared points, pi over 2 plus pi k, where k belongs to set z. So far, so good?
Yes.
Yeah.
What about the range? We already discussed definitions and properties of many functions. And if you just, let's say, keep right now in your mind a definition of the tangent. Tangent is a ratio of y coordinate to x coordinate, where x and y coordinates are coordinates of the endpoint on the terminal side of the angle under symbol of the tangent. So definitely, if x is 0, we cannot discuss that because we cannot divide by 0. This is why for all vertical quadrantal angles, x coordinate on the endpoint on the terminal side will be equal to 0. This is why tangent is undefined. But tangent is defined for many angles, basically for all other angles which are not vertical quadrantal. And it can be equal to any real number. You already learned that in your 3 class. This is not the function which has restrictions for the value of the function, as we had, for example, for members of cosine family or sine family, because for any angle, sine or cosine value cannot be greater than 1 and cannot be less than 1. But tangent can be equal to any number. This is why domain is limited. It has set R except all vertical quadrantal angles, but range has no restrictions. It is equal to set of all real numbers. Now, definitely, we can describe family of tangents using, as we say, modified formula. For example, if you look at the formula for modified, just 1 second, I will write it down. For modified members of tangent family, it looks exactly in the same way as for families of sines and cosines. Can you see the resemblance?
Yeah.
Yes.
Yeah.
And we have same parameters here. A parameter, omega, phi, and k. And practically all these play same role as they played for other families except A. Only 2 families have amplitudes, families of sine and cosine. All 4 others, they do not have amplitudes. They all will have that coefficient A. But only, again, two families have amplitudes. If let's say we write down y equal tangent x to identify these parameters, a is equal to 1, omega is equal to 1, phi here is equal to 0, k is equal to 0. Even though we have a value for a is 1, I cannot say anything about the amplitude because tangent x and all other tangents, they do not have amplitudes. Can you please write it down that only two families of functions, sine family and cosine family, have amplitudes. For other families of functions do not have amplitudes. This why don't even say anything about amplitude, or if you decide to say something about amplitude, you need to write amplitude none, or just this function does not have an amplitude. If we talk about period, definitely omega here is affiliated with the period, but for tangent and cotangent families, formula for the amplitude is different. It is pi over omega. For other families, it is 2 pi over omega. But for tangent, it is, and cotangent, it is pi over omega. This why, for example, for our basic tangent x, it is pi over 1. So period is pi. So there will be no vertical shift and no phase shift. This why I'm going to write it phase shift, none. Here, vertical shift, none. And we already discussed vertical and horizontal shifts for sines and cosines. It is working here for tangent family absolutely in the same way. If we talk about phi not equal to 0, it will be a phase shift in this in the direction opposite to the sign of phi. If phi is positive, it will be moving to the left horizontally. If phi is negative, it will be moving or shifting to the right. But k is affiliated with the vertical shift, so it will be moving in the same direction as this sign tells us to move. So if k is positive, that graph will be shifted up. If k is negative, it will be shifted down by k units. I'm ready right now to sketch the graph of tangent. And you again need to show your graph in at least 2 cycles. The length of each cycle is equal to the period. So the length of your cycle for tangent x should be equal to pi. This why, please sketch x-axis and y-axis. And show the length of pi. Do that on both sides from 0 on x-axis. And I can even show this on more than 2 cycles because the period is here quite small. You can see I showed here multiples of pi. Right now, I will be working mainly right now with the interval from 0 to pi. From 0 to pi, it is one cycle. I'm going to divide this again into 4 congruent pieces as we did before, and I will label all these points. Right in the middle between 0 and pi, we have pi over 2. In the middle between 0 and pi over 2, I have pi over 4. In the middle between pi over 2 and pi, we have 3 pi over 4. So each small interval has a length of pi over 4. And actually, I can spread this into both directions from 0, because in the interval from negative pi to 0, I will have similar points only with minus pi over 4. I am moving from 0 to the left. Minus pi over 2, minus 3 pi over 4. If you like to continue to the right from pi to 2 pi, or to the left from negative pi to negative 2 pi, you can do that very easily, counting each time, using pi over 4 in your mind as the length of each interval. So first show this geometrically, dividing these intervals into smaller pieces. You can see what I did. I have all these pieces right now. And now I will be counting by pi over 4. So look what I do. At pi over 4, basically I have 1 times pi over 4. Pi over 2 is 2 times pi over 4. Let's say pi is 4 times pi over 4. Next point is 5 pi over 4. Next one is 6 pi over 4. But 6 pi over 4 is 3 pi over 2. Next point, 7 pi over 4. And 2 pi is actually 8 pi over 4. And I can do absolutely the same thing on the other side, from negative pi to negative 2 pi. Please do that as we did with the right piece. So it will be negative 5 pi over 4, negative 3 pi over 2, negative 7 pi over 4. And I labeled all these points. And I don't need to label many points on y-axis. What would be the next step? Please sketch asymptotes. Asymptotes are running through here are the multiples of pi over 2. Why do I say? Look at, just consider these examples like in one revolution. First asymptote should be running vertically through pi over 2. Another through 3 pi over 2. Tangent is pi periodic function. Can you see what I sketched? I already sketched that vertical lines through these two bad angles for tangent. Do the same thing on the other side. So another asymptote will be running through negative pi over 2, because all asymptotes here are also located on the distance of pi between consecutive asymptotes. So which means on the left side from 0, they will be running through negative pi over 2 and negative 3 pi over 2. These are all your asymptotes on this graph. Definitely we can continue with asymptotes moving more and more further on to the right side from 0 and to the left side from 0. But it is not a necessity because here we already have more than 2 cycles. And I will be right now working with the central piece between 2 vertical asymptotes, which are x equal to negative pi over 2 and x equal to positive pi over 2. Right now, you need to show significantly important points for that tangent. There are not too many. Let's start with the 0. 0 radians. What is the value of tangent of 0? Guys, I'm waiting for your reply.
0.
Is it an answer or a question?
Answer.
0.
It is 0. So, which means we have already 1 point, which is 0, 0. Okay, what is the value of the tangent of pi over 4?
That's 1.
It is 1. So please, there's another point, which is 0, here pi over 4, comma 1. What is the value of tangent of negative pi over 4?
-1.
Negative 1.
Please, there is another point. Parenthesis negative pi over 4, comma negative 1. And knowing that we are having 2 consecutive asymptotes, here graph of the tangent will not cross or touch this asymptote. Look what I am getting as a graph. This graph can be continued forever, more up and more down. This is quite typical. Here I showed 3 important points. I showed these asymptotes, and this is one only piece of that graph between 2 central asymptotes, because now we can spread this graph to the right side and to the left side, moving from central piece to the right or to the left. And this all the time will be actually same curves on the right side or on the left side, because again, tangent is pi periodic function. If you like to show, let's say, 1 point, which is corresponding point for the origin, you need to count on the x-axis 4 pieces each by pi over 4. So which means we are moving from this point, which is right here, 1, 2, 3, 4, and I am here stopping at pi. Yeah, and I know tangent of pi is 0, which is correct. I made that point quite thick. You can see. If you need to now get the similar point for x equal to pi over 4, start counting 4 pieces from pi over 4 to the right. So it will be from pi, it will be from pi over 4. I'm counting 1, 2, 3, 4. And this will be again value equal 1 for this time pi over 4. This is another point which is right there on the graph. If you need to do this for negative pi over 4, start counting 4 pieces from negative pi over 4 to the right, and you for sure will end at 3 pi over 4, and for this value, it will be negative 1 for y. So we have, again, 3 points right here, and I'm going to sketch another curve. It reminds us a graph of cubic parabola, y equal to x cubed. And you can continue. Please do that a little bit more, going to the more right a little bit and to the left. I will do that and I will show it to you. Can you do that independently for about 2 minutes? You are obligated to show this in 2 cycles. I just here had a little bit more space. This is why I'm showing this on more cycles. I will show this to you right now. At the left end and at the right end, you can see I have just part of that curve because I did not have many points at these intervals. But you can see that these pieces also remind us complete pieces between three. You have complete pieces in 3 cycles here and partially in 1 and the other cycles. This is your graph. It is same shape over and over and over, and we have infinitely many of these pieces between consecutive asymptotes. You can continue again forever, moving to the right and to the left on this graph. Did I remind you something? Did it come back to your mind, guys?
Yes.
Okay. Basically, this is all what I wanted to talk about this function right now, because again, vertical, horizontal shift determination of the period, we already discussed the formula for the period, which is slightly different, but vertical and horizontal shifts are working absolutely in the same way as they work for other functions, which we already discussed. Right now, I would like to ask you to write down the other topic, and this is about inverse trigonometric functions. First, I would like to say a few words about symbols which we use for these functions. Unfortunately, in the trigonometric textbook, which you probably used, there was only one symbol and not actually the main symbol for these functions, because all these functions, inverse trigonometric functions, they have common name like arc functions. So this why I would like to write down right now just symbols for these functions to show you possible symbols. The first function is inverse sine, which you probably wrote in that way, right? Sine minus 1 of x. It is not negative first power, no way. This is the symbol of inverse function. And as you know, we are using f minus 1x also as a symbol of inverse to f function. But it has another more traditional symbol, which was much older. It is symbol much older. And actually in your textbook, I would even will tell you about the page on which you had this symbol. And this symbol, arc sine x, is being used very often in many textbooks. Arc sine x. It is same thing. This is why we call it, actually, you can say inverse x, but I will be using its traditional name. It is arc sine x. Even if you use that sign with -1 symbol as inverse sign, the name of that is arc sine x. This is the main name. So inverse sine, it is like a nickname of that function, but arc sine x is official name. In the same way, you can talk about all other arcuses like arc cosine or arc cosine x or arc tangent and etc. Arc secant, arc cosecant, and all others. To show you that actually I have good reason for that, I really like to ask you, just 1 second, I need to find that page. On page number 321 in your textbook, you can look at the problem number 78. Can you please do that quickly? Page number 321, problem number 78. And actually, I really like to solve that quickly, that problem. And again, it is on page 321, problem number 78. You need to say if this statement is true or false. And it states, if arc sine x equals 0.5, then x equals pi over 6, if it is correct or no. We will talk about that just a little bit later. So just I decided to show this right now to you because I really like to tell you that yes, it is written in that way, like arc sine of x. Okay, so what I'm planning to do right now, and I'm going to talk about very important things. The meaning of that arcuses. When we talk about direct sine x, let's say we are considering the function which is y equals to sine x. We have here two variables, x and y. I really like to tell you what they indicate. Here, y equal to sine x. X is playing a role of what kind of variable? Is it the independent variable?
Yes.
Yeah.
Is it representing a number or angle?
Yes.
X is a number or an angle?
Angle.
Angle. So X is the angle. What about Y? Y is another variable. Is it an angle or a number?
Number.
Number. And this is a direct function. This is a direct function. But what about its inverse function? Inverse function also can look like y equals to something. And let's say I'm writing down them side by side. Y equals to arc sine of x. And now we need to discuss this in the same way. What about this x? Don't forget, these two functions are inverse to each other. What can I say right now about variable x, which is an independent variable here? Is it an angle or a number?
Number.
Number. Because if we have two inverse to each other functions, that one which was in the original function was an angle, it becomes a function in the second case. So now y is the angle and x here is a number. X and y here play different role, not as they were in the original function. This why it is absolutely natural to think about the nature of, let's say, arc sine. What do we have for arc sine as a function? Result of that relationship, which is the function, is the special angle for which sine will be equal to that number x. So practically here, if we need to talk about arc sine, I'm talking about now problem number 78, and actually we can write it in that way. Arc sine of pi over 6. Here, even though under symbol of arc sine, I have pi over 6, which looks as an angle. You cannot treat this as an angle. This is practically the same thing. Grab your calculator. This is a number pi, which is about 3.14, divided by 6. So practically, just 1 second, you are grabbing your, let's say, calculator. Arc sine is located right above button, which says sine. But before you do that, can you please check your mode? Be sure, press button mode. Be sure that your radians are highlighted. And you are coming back, second button and mode button, and you are using that second button again and sine, because you need to have arc sine, and you are entering pi, which is again second button and button with the corner, because you need pi. Just 1 second, please, I will show it to you. This is how you are entering this into your calculator. Because for you right now, pi over 6 is not an angle. It is the number approximately equal to 3.14 divided by 6. And you push enter, and you are getting here 0.551. And it is not equal to 0.5. So this statement, which you had in the textbook in problem number 78, if it is true that if arc sine of x equal to 0.5, then x is equal to pi over 6, is incorrect. This is the false statement. False. But which one will be correct? If you have another problem, so I'm putting star here, and what would be correct? If you had arc sine of 0.5 or 1/2, it is up to you if you like to write this in decimal. What is the meaning of arcsine of 0.5? It is the main angle for which sine should be equal to 0.5 or 1/2. Which angle in the first quadrant has sine equal to 1/2? It is pi over 6. This is a true statement, but the previous one was incorrect. Because all arcuses are main angles, because even in one circle, in one revolution, I can find at here two angles for which sine will be equal to 1/2. And only one of these angles will be a main angle, or we call them reference angles. So this why, talking about this particular function, like y equal to arcsine x, I need to talk about domain and range. You probably remember one thing, and I'm going to right now show only half of the circle, the right half of the circle. Just 1 second. Right half of the circle. This time we should not talk about whole unit trigonometric circle. And I'm ready to write down domain and range for arcsine. Domain and range. Don't forget, domain is values of x's. X here represents values of sines. If you remember, any sine of any angle could not be greater than 1, could not be less than -1. This why, if you have x as independent variable in your arcsine function, doesn't matter how it is written like inverse sine or traditional arcsine, x can only be equal to any number between -1 and +1, including endpoints. At the same time, R here is a set of y's. Y's here are angles, but we are talking about main angle, and this main angle can be only from shown part, shaded part of the circle. It is between -pi/2, which represents fourth quadrant, and the first quadrant if we move from down coming up. So this what we have. This is the segment between -pi/2 and +pi/2. Another thing what I like to mention here is the formula, which is unfortunately not shown in this section about inverse trigonometric function, which is section 7.8, because it has quite not really many interesting problems. This why, let me show you this actually existing formula, because it can help you to solve many problems with arcsine. And I'm going to box that formula. Arcsine of -x equals to minus arcsine of +x. This why now we can talk about some problems. An example, what would be arcsine of +1, ladies and gentlemen? What I need to recall, that it should be angle or from the fourth quadrant or from the first quadrant for which sine is equal to 1. Which angle in the declared segment has sine equal to 1? Is it pi/2?
Yeah.
I think everyone understands that you all have to go back to values of trigonometric functions and seriously review this material because I'm really not satisfied with what I hear. Okay, what about, let's say, arc sine of negative square root of 2 over 2? Arc sine of negative square root of 2 over 2. If I were you, I would first apply that formula, which I boxed. It will be minus arc sine of positive square root of 2 over 2. And I'm expecting negative answer. So now just pay attention to positive part of arc sine of square root of 2 over 2. So arc sine of square root of 2 over 2 is the main angle, and sine should be positive for this angle. So it will be from the first quadrant, for which sine is equal to square root of 2 over 2. Is it pi over 4?
Yes.
Yeah.
So the answer here is negative pi over 4. And I am done with this problem because, again, all arcuses are main angles. I do not have time right now to talk about arc cosine and arc tangent, and I'm planning to do that the next time, and I will devote tomorrow's lecture, entire lecture, reviewing this material with arc sines, arc cosines, arc tangent, and other arcuses. Unfortunately, your book does not have enough material, so I will be demonstrating you other examples as well. And I like to have really good review tomorrow for this material because this material is quite important. So I hope you had time to, I really apologize. Just 1 second, please. This is my alarm. I'm done for today. And would you let me finish today's lecture?
Yeah.
Yes.
Okay, guys, I again will send you a link to the YouTube video for this lecture, and I will see you tomorrow. Everyone have a nice, beautiful day. Okay, bye.
Bye.